students, in physics, now we are going to see another experiment in the section heat. What it is about? Determining the thermal conductivity of rubber. You know, rubber is a rare conductor. It doesn't conduct heat very fast. So, for a rare conductor like that, how are we going to find the conductivity? It's almost the same procedure, but slightly small changes or differences are there. See what we are going to do. We will take a rubber tube and we will roll it like this. We will make it into rings and take a calorimeter which is lagged properly so that it doesn't receive or give heat to the environment or from the environment. Then through this rubber tube, you send some steam, hot steam. Measure the time and send the hot steam. Right, when you start sending the hot steam, start the stopwatch and measure the time for a certain time. The steam will be going through this and will go out. And what you see here is the cross section of this rubber tube. Let me draw that bigger. This is the internal circle, internal surface. This is the external. This is the external surface. So, this is the thickness of rubber tube. Now, what happens through this rubber tube? You are sending steam. So, when you are sending steam through this rubber tube, this surface is going to be 100 degrees. Assuming steam is at 100 degree, right? The internal surface of the rubber tube is going to be at 100 degree. What will be the temperature of external surface? That's the temperature of this water. Let's say when you are starting the experiment, external temperature is, let's say, 28 degree. Okay. Now, what will happen? Since there is a temperature difference from the higher temperature to the lower temperature, the heat has to flow. So, heat will be flowing like this. Right. When heat flows like this, what will happen to this temperature? This temperature will increase. Why? The heat comes out through the rubber tube. Who gains that heat? The water, and calorimeter is going to gain that heat. So, the temperature of water and calorimeter have to increase. This 28 degree will start going up. Let's say we wait until it goes up by 5 or 6 degrees. We stop the experiment when it is 34 degrees centigrade. Just assume like that. Internal temperature doesn't change because we get new steam. It's a flow of steam. Right. So, because some heat goes out, the temperature internally is not going to change because new steam keeps on coming. Yes, that's always 100. So, you know, through a substance, if heat is being transferred like this, we have the formula. The rate at which heat is transferred equals to Ka delta theta over thickness or the distance. Right. That's a rate. And you know the time it has taken. So, the rate into time is going to be the heat transferred through this tube. Ka delta theta over thickness. Thickness, how do we find the thickness? Now, K, let me write that here. Ka delta theta, theta 2 minus theta 1 over the distance or thickness. This is the rate into time. This is going to be the amount of heat. This is going to be the amount of heat transferred out. K is the conductivity that we have to find. A, how do we find A? Look at this. Right, if I mark these points, right, we can take a pen and mark here from which point to which point the rubber tube has been submerged into the water. Then after the experiment, you remove, there will be a like, you tie this with a thread. So, remove that thread and extend it, right. Then you will get a tube like this. So the surface has to be 2 pi r L. 2 pi r is the circumference of this circle, L is the distance. But we have an issue here, which r we are going to take. Are we going to take internal radius or external radius? We will take the average radius. Then you have to measure the internal radius. Let's say internal radius is r1, external radius is r2. Then the area here, A is going to be, the A is going to be 2 pi r1 plus r2 by 2 into L, the average radius. Theta 1, theta 2 you can measure with this thermometer, initial temperature of water, and when you are ending the experiment, what's the temperature? T is going to be the time it has taken. Only K is the unknown. So this is the amount of heat, quantity of heat that has been transferred from the tube or from the steam to the water and calorimeter through the rubber tube. Now what do we do? Who gains this heat? Water and calorimeter. So how do we write the formula for the heat gained by water and calorimeter? Water and calorimeter gained MCCC MWCW. This is the heat capacity of both. This is for the calorimeter, this is for the water, into theta 2 minus theta 1. Hold on. What would be the D here? R2 minus R1, right? R2 minus R1. D is going to be R2 minus R1. Thickness. Right. So, MCMW you can measure with a chemical balance or 3-beam balance. CC is usually considered to be 420, it's copper. Water specific heat capacity is 4200. Theta 1, theta 2 you can measure. Right. So, with these readings, we can equate both. Heat released through the rubber tube is equal to the heat gained by water and calorimeter. Equate them. All the readings are known. Only K is going to be the unknown. You can find K. Clear? This is what we do. The heat released through a rubber tube of length L, internal radius R1 and external radius R2 is absorbed by calorimeter and stirrer of mass MC and water of mass MW, resulting in a rise of temperature from theta 1 to theta 2. Clear? So see, I am writing the formulae again. Heat released through the rubber tube equals to K. See, this is my A. This is the temperature gradient. This is time. Time you can measure with the stopwatch. Heat gained by the calorimeter is equal to this. This is the heat capacity. This is the delta theta. You equate those two. Heat released, but we have an assumption here. What is the assumption? From the calorimeter and its contents, there is no heat transfer to the environment. Right? There is no heat loss to the environment because we have lagged it properly. So there is no heat transfer happening to the environment. In that case, you can assume these two to be equal. The heat transferred or heat released through the rubber tube and the heat gained by water and calorimeter are equal. Materials and apparatus, you can see a calorimeter with lagging, proper lagging you need. Rubber tube with thick walls. Why it has to have thick walls? Because otherwise you can't, the measurement error will be high, right? If it's a very thin wall, the measurement error will be high. So to have lower measurement error, you have to have thick walls. And approximately 25 centimeter length. Why we say approximately 25 centimeter length? See, if you take very short length of rubber tube, then the area is going to be less, right? 2 pi r L. L is going to be shorter. When the area reduces, K A d theta over thickness into the time. When area reduces, the heat that is going to be transferred, the rate at which heat is being transferred to the water will be less. So if you want 5 or 6 degree increment in the temperature, you will have to wait for a longer time. Longer time. Longer time will give you errors. If you want to finish in shorter time, why longer time gives errors? Heat loss to the environment will be there. But if you want to finish in shorter time, then the temperature rise in the water will be less. Why? Since you are taking a shorter piece of rubber tube, it doesn't release the heat faster because area is less. Therefore, the heat transferred to water will be less. That's why 25 centimeter is a reasonable size. If you take two lengthy ones, rolling them and submerging that in the water will be difficult because calorimeter you won't get so big ones, right? So 25 centimeter is usually considered to be optimum level. Doesn't exactly have to be 25 centimeter. Around that, even 30-35 centimeter is fine. That's okay. A piece of string or thread. Why do we need the thread? To tie that. After you make the rings, you have to tie it, right, with the rubber tube. Otherwise, how do you submerge it? Thermometer. Traveling microscope. Why do we need traveling microscope here? Because to measure the internal and external diameters of this rubber tube. Can't we use a vernier caliper here? No, because if you take it into the vernier caliper, it changes the shape, right? It's not stiff enough. It's not rigid enough, right? So, since it is not rigid, you can't use a vernier caliper to measure the internal external diameters. So, the ideal instrument for that is traveling microscope, which doesn't change the shape of this rubber tube. As it is, we can measure the internal and external diameters. Meter ruler. Why do we need meter ruler? To measure the length of that rubber tube. After we finish the experiment, what do? We remove the thread, extend it, take the meter ruler and measure the length of it. Triple beam balance. Why do we need triple beam balance? To measure the mass of water and calorimeter. Stand. Why do we need stand? To fix these. Stopwatch to measure the time. Steam generator to generate steam. And also you can add a Bunsen burner as well. Method. Let the water boil in the steam generator. Measure the mass of calorimeter with stirrer. Calorimeter and stirrer. Don't forget stirrer. In the exam, if you don't write stirrer, you might lose marks. Make the middle part of the rubber tube, approximately 25 centimeter, into small rings and tie it with thread. Connect the tube with steam generator. See, you connect the tube with the steam generator and keep it outside the water for some time. And wait until the steam is generated. When the steam starts flowing, give it some time keeping it outside the water. Why? The internal surface of this rubber tube has to come to 100 degree. It won't immediately happen. It might take few seconds. After the steam starts going through, still it might take few seconds for it to come to 100 degree. Why? In the calculation we assume, look at this, we assume internal surface is at 100 degree. So, after steam starts going through this, give it some time for the internal surface to reach 100 degree. After that only, so after the steam starts coming out, wait for a while, then only you are going to submerge this rubber tube part into the water. Don't forget that. Fill the calorimeter with sufficient amount of water and keep the stirrer and the thermometer within it. Measure the initial temperature of water, theta 1. After the steam starts to come out at a constant rate, submerge the rings of rubber tube into the water within calorimeter. Simultaneously start the stopwatch also, because you need the timing. From the time you are submerging it until you get the final temperature, you need to measure the time. Stir it continuously. When water's temperature increases by around 5 degree, note down the stopwatch reading and the temperature of the water. Approximately 5 degree. Right, don't take too small temperature differences because the reading error, percentage error will be high. Don't wait until the temperature increases by much bigger amounts because the time will be bigger, can have errors. What errors? The loss to the environment, heat loss to the environment will be high. Measure the mass of calorimeter with water and stirrer, MC plus MW. Measure the length of submerged rubber tube. Measure the internal and external diameters of rubber using travelling microscope, right? That's what the steps are. Okay. Now, while doing the experiment, I'll further explain each step again. You have to observe carefully. Shall we start doing the experiment now? So, the apparatus required for this experiment include, you can see this is the steam generator, or you can say boiling tube, right? What do? We fill this with water and then we heat the water, right? When the water reaches the boiling point, which is approximately 100 degrees, you'll get steam from this end. And you know why we keep this tube? To maintain the pressure at atmospheric pressure within the boiling tube. So you know this tube has to go in as long as it touches the water. It has to be below the water level, right? Then only you can maintain the pressure. I have explained this in the previous experiments also, right? What will happen when the steam is being generated? The steam needs more space than the water. It expands. Then the pressure will increase inside, right? So by keeping this within the water level, when the pressure increases, then the water will not have sufficient space to stay inside. Then you can see the water climbing up this way, right? Water will climb up so that it takes sufficient space for it and maintain the pressure at the atmospheric pressure within this boiling tube. So this is the steam generator or boiling tube. This is water. This water only we are going to use for generating steam. And we use a 3-beam balance to measure the weight of calorimeter and stirrer, and then calorimeter, stirrer plus water, because we need to do the calculation how much of heat has been transferred. For that we need the mass of calorimeter, stirrer and water. We need a 3-beam balance for that. We need a stopwatch because time is important. How long we keep it within the water, how long we keep the tube within the water. To measure that, we need a stopwatch. And this is the rubber tube. This is the rubber tube. This rubber tube only we will be keeping within the water. Part of it we will keep, we'll roll it, and a small part, maybe around 20 to 25 centimeters, we submerge within water, and through the rubber tube, steam will be sent across, right? So this is the rubber. To measure the temperature of water and calorimeter, we need a thermometer. 0 to 50 thermometer is also okay. Anyway, I'll be using 0 to 100 thermometer, because why I said 0 to 50 is okay. You are starting at room temperature, and you are going up to approximately 10 degrees above. So room temperature is around 27, 28 degrees, or even if it is 30 degrees, you go up to 40. Sometimes they ask, is it okay to use 0 to 50? Yeah, 0 to 50 scaled thermometer is also fine for this experiment. This is the calorimeter. This is the calorimeter with the stirrer. This is a stirrer. So in this only we will have the water, and through which we will be sending this rubber tube with steam. You can see very well it's insulated. So the heat loss to the environment is prevented. Also we will be keeping it on another insulator. You can see a regiform piece. So you keep on that, so that any heat conducted to the table, heat loss through the conduction is also prevented, right? Then we have a stand here, because when we do this experiment, it's easy if you can fix the thermometer within the water. To fix the thermometer, we use this stand, Bunsen burner, tripod and a wire mesh. This is a travelling microscope. We have already seen how to use travelling microscope when I did the experiment measuring equipments. Here, why do we need this? I told you we need to measure the width or the thickness of this rubber tube. I need to measure the thickness of this rubber tube, right? So this thickness, since like when you press it, it can get deformed. You can't measure it with any other instruments. It's easy, and you can measure it precisely with a travelling microscope, right? Since it is a deformable rubber tube, it's easy if we measure the thickness of it. We can measure the internal width or internal width, yes, and the external diameter, external diameter we can measure using the travelling microscope, right? In the measuring equipments, I have shown you how to use a travelling microscope. So here we will not be spending too much of time explaining how to use traveling microscope. We will just use the traveling microscope, get the thickness of this rubber tube. Clear? So this is all the apparatus we need to do this experiment. What we will do, first we will fill this with water and we will let it heat it. As I stated earlier, I have taken the calorimeter and the stirrer. Calorimeter and stirrer. You can see. So let's get the weight of these two together, calorimeter and the stirrer. Let's change it 100 by 100. It's less than 100. Make it 0. Change it 10 by 10. 20, more than 20. 40, more than 40. More than 60. More than 70. But less than 80, you can see. It's less than 80. So keep it at 70. Now 1 by 1. 72. 74, it's more than that. 76, more than that. 77, there is a small change, but still more than that. 78 is too much. So it has to be in between 77 and 78. Yes, it is at 77.4 grams. 77.4 grams. The mass of calorimeter and the stirrer together, 77.4 gram. Let's write it down on the piece of paper. The mass of calorimeter and stirrer together, we got 77.4 grams. Let's write it down here. MC 77.4 grams. What next we have to do? We have to fill that with sufficient amount of water. When I say sufficient amount of water, I told you we are going to submerge like approximately 20-25 centimeters of the rubber tube into the water, right? So have sufficient amount of water to submerge this rubber tube within that. With that amount of water, again we have to measure the mass of calorimeter, stirrer and water together. That's what is MC plus MW is. So let's see how much is that. Let's fill the calorimeter with sufficient amount of water. Right? Now let's measure the weight of it. Make sure the stirrer is also inside. I kept the stirrer also inside. Yes. With that. But if the stirrer has a, say, rubber cap or something, rubber handle or something, usually from the stirrer you can remove it. Make sure you remove that only the copper part of that is measured. So we make an assumption when this stirrer and calorimeter get heated, we assume that rubber cap or rubber handle doesn't get any heat. It's an assumption. But actually it's a small error. There will be a small amount of heat that will be transferred to that rubber cap as well. But we assume it doesn't get absorb any heat, right? So now what I have here, calorimeter, stirrer and water. Let's measure the weight of it. Let's bring it to 0. Bring all the scales to 0. Check 100 by 100. It's more than 100. More than 200. More than 300 as well. It's less than 400. So let's keep it at 300. Check 10 by 10. More than 310. More than 320. There you go. It's less than 330. So let's keep it at 20. Now increase 1 by 1. It's more than 325. More than 328. It's It's more than 329 as well. There's a small change, but still it's above. We'll see where it balances. Yes, it is at 329.8 grams. 329.8 grams. Let's write down this also in our sheet of readings. So MC plus MW, we have got 329.8 grams. 329.8 grams. What next? We have to measure theta 1 and theta 2. Theta 1 is the initial temperature of water within the calorimeter. And what is theta 2? After we have sent the steam through the rubber tube, which is submerged in the water. After a while, what is the end temperature? That's what we do. We submerge the rubber tube. We send the steam through that. Approximately 10 degrees high is what we expect. After you remove the rubber tube also, you have to keep stirring it and wait until you see the maximum temperature it goes to. Sometimes even after you take the rubber tube, it might slightly go up because until it stabilizes, until it comes to a stabilized temperature reading, it might take a while. So wait until that and see what's the maximum temperature recorded. That will be theta 2. Right? So shall we check theta 1 now? That is the initial temperature of water, theta 1. Let's measure the initial temperature of it. Initial temperature. It is 27 degrees. 27 degrees is what we see here. So the initial temperature of water and calorimeter, which is theta 1, is 27 degrees we have got. Let's write it down here, 27 degrees. Right, now we can generate steam and send it through the rubber tube, submerge the rubber tube within water for a few minutes and then check the temperature theta 2. What is L? The length of rubber tube which was submerged within the water. So at the end of experiment we can measure that. What is T? Time. How long we were sending the steam through that time. So we will be using a stopwatch for that. So these three we'll write down at the end. As I mentioned earlier, I have made the setup. You can see this is the calorimeter with water and stirrer. I have kept the thermometer and fixed it with a stand. It has been insulated. You can see it has been insulated. And also in the bottom also I have kept an insulator here. You can see. So it's insulated. Now what we are going to do? We are going to generate steam. How do we generate steam? Let's fill this with water. Here in this you can see the steam level. In this you can see the water level. When we fill this with water, you can see the water level. Let me show it to you. Can you see here? This is where the water is. This is where the water is. Right. Why we need that water level is then, you know, when I keep this cap, when I keep this lid, I know whether this tube goes up to the water level or not. Can you see now? The tube is here. This is the cap level. The tube is here. So better I'll fill more water. Better I will fill more water up to here. Yes. Right. Now the water level has gone above this, and we saw the tube will go underneath that. Now let's close it. Let's keep it on the burner on top of the wire mesh. Also, you can see I have made a small round shape. Now this round shape is what we are going to keep within the water, what we are going to submerge within the water. Yeah. After we submerge it, we can mark the points. From which point to which point it was submerged, I can mark it. Right. For the moment, we will keep it outside. Now what I am going to do, let me start the Bunsen burner. Let it get heated. And then you can see whether the steam comes out or not from here. So after you start getting the steam, don't immediately submerge it, just keep it for a while so that the internal walls of this tube, they also get stabilized at 100 degree. Because when the steam comes, steam will be at 100 degree, but the internal walls of the steam might be less than 100 degree. Little by little only they will come to 100 degrees. So give it some time, let the steam go out for a while, then you take it and submerge it here. Right? So let's start the Bunsen burner now. Now you can see I have started the Bunsen burner. So water will get heated. It will take a while. Just keep waiting until the steam starts to come from this end. Once the steam starts to come from this end, as I mentioned, wait for a while and then you can submerge it. After you submerge it, make sure you keep stirring it and check the temperature. After you take it out also, don't immediately record the temperature. Just keep stirring it and wait until you see the highest temperature. Read that highest temperature and record it. Right? Now let's wait until we generate steam from this. Students, you can see the steam started coming. I have been waiting for a few seconds until the heat keeps on going. Now the temperature inside the tube can be assumed to be 100 degree. How do I know it's 100 degree? Because of this tube, I am maintaining the atmospheric pressure inside. So with the atmospheric pressure, the boiling point is 100 degrees. We know that, right? So the steam comes at 100 degree. Since I maintain the steam for a while, now the internal wall, that means that this tube's internal wall is also assumed to be at 100 degree. Now what do I do? Let me take this tube. Right, there you go. I have submerged it. Let's keep mixing it. Let's keep stirring it. We have to monitor the temperature until it comes to approximately 10 degrees above where we started. 10 degrees above where we started. You saw that I started the stopwatch also. When I submerged it inside, I started the stopwatch. Then when I take it out, I'll stop the stopwatch. So we know for how long we have been keeping it inside. You can see the temperature is coming close to 30 here. It's coming close to 30. We started at 27. Let's wait until it goes to approximately 36, 37 degrees. The temperature is rising. Temperature is rising. You can see. You can see the temperature is now around 34. It has passed 35 now. (36). Maybe we can stop at 37 degrees. Check here, it's almost 37 degree. At this point, let me stop the stopwatch and take it out. Still don't get the reading right now. Let's keep stirring it until you see a maximum temperature. I can see it has gone up to 38 now. 38. Keep doing it. It's stable at 38. Let's wait for some more seconds. You can see here, it's 38. It's 38. So it has almost stabilized at 38 degrees, right? Let's check for some more time. Yes, it doesn't change. So the maximum temperature we have got here is 38 degrees. Also, see, these are the 2 points I can mark. I have marked it on the tube from this point to this point. See, this is the point that I have marked. That means this part of tube was within the water, this part. But that's the length I have to measure. That will be L. Right. Let's get the measurement of that length as well. You can see that starting from here, all this distance up to here. Right. So we got theta2 now. We'll get L as well. Time we can see here, how long we kept the tube inside the water. It's 3 minutes and 12 seconds. 3 minutes and 12 seconds. It's 3 minutes, 12 seconds and then 50. So we can say almost 3 minutes and 13 seconds. 3 minutes and 13 seconds. 3, 12, 50, right? So that's almost 313. Right? Now let's remove this round and see how much is the length of tube that we have kept inside the water. Students, you can see I marked 2 points. See, this is where one point is. You can see I marked with pencils here. This is where one point is. And the other point is here. You can see it's here. I marked with pencils. So now let's get the length between these 2 points using the ruler. So the length I am getting starting from 0 here and up to here, it's 26 centimeters I am getting. 26 centimeter. So the length of tube that we submerged within the water was 26 centimeter. L is 26 centimeter. Shall we write down all these values? Initial temperature was 27 and the end temperature was 38 and the length we have used 26 centimeters. Let's write down all this. Now theta2 we have got 38 degree. The end temperature of water and calorimeter 38 degrees centigrade. Length of rubber tube that we submerged into the water 26 centimeters. 26 centimeters. And T, the time, how long we were keeping it within the water, 3 minutes and 13 seconds. 3 minutes and 13 seconds. Now what is the other measure we need? We need to measure the internal diameter, external diameter of the rubber tube that we submerged. I'll show you the internal diameter and external diameter. So you can see now this is the rubber tube we have been using. So what I meant is we had to find the internal diameter. See, internal diameter. Internal diameter, internal. And external diameter, external diameter. If you get the internal diameter and external diameter, you get the difference. That will be twice the thickness, right? Twice the thickness. For that only, I am going to use the traveling microscope and get the reading. So as I mentioned earlier, we will not be spending time explaining how to use the traveling microscope, how to get the reading and all, because we already are familiar how to use traveling microscope. So I'll get the readings and use them in the calculations. Right? So that's all in this experiment that we have to get as readings. Now we'll see to the calculation and find what is the thermal conductivity of this rubber, which is usually an insulator. What is the thermal conductivity of this rubber tube is what we are going to calculate and see. Right. The readings I have got have been tabled here. Mass of calorimeter in water, initial temperature of water, final temperature of water, length of rubber tube, internal diameter of rubber tube. Its diameter. I have taken the diameter with the traveling microscope. Yeah, I have not shown that because we have already seen that in the light experiments, in the optics experiments we have seen that. Also, there is another separate area called measuring equipments. Again, I'll explain the traveling microscope in detail, how to use it. So here I did not show you in detail how the diameters have been measured. Only thing you need to know, traveling microscope has been used to find D1, D2. From this you can get R1, 3 millimeter, R2, 4.3 millimeter. 3 minutes and 13 seconds means 3 into 60, 180, 193 seconds. Time. So we can write the formula. Q equals K. A is 2 pi R. R has to be R1 plus R2 by 2, right? That is 4.3. 3 plus 4.3 by 2 millimeters. So into 10 to the power minus 3 has to come. 2 pi r L. L how much? 26 centimeters. 26 centimeters. 26 into 10 to the power minus 2 into temperature gradient. Internally it's 100. External temperature, we'll take the average. 27, 38 average. 27 plus 38 by 2 is 50, 65, 62.5. No, 32.5. 32.5 degree is the average temperature. 32.5. 32.5. Thickness has to be R2 minus R1. 4.3 minus 3 into 10 to the power minus 3. Right? Into time. Time 193 seconds. This is the heat released. Equals to MCCC. MC 77.4 grams. CC 420 for copper. MW, subtract and get it, MW here. When you subtract it, 252.4 grams. 252.4 grams. 10 to the power minus 3 into 4,200 water into delta theta minus delta 2 minus delta 1 or theta 2 minus theta 1, 38 minus 27. 38 minus 27. We have to solve this. Let's see. Let me cancel all that I can cancel here. Here's the 10 to the power minus 3, 10 to the power minus 3. Gone. Then, here we have a 10 to the power minus 2. With this, 10 to the power minus 2 is out. Here also we have to cancel it. See, 1, 0 and 10 to the power minus 3 will be 10 to the power minus 2. On the other side, you have 10 to the power minus 2. Right. Now, the 2 and 2. Is there anything else we can cancel? Not sure. Let's write it a simplified version and see. K 22 by 7, 7.3, 26, 67.5 over 1.3 into 193 equals. Look at this. If you take 42 outside, a 0 has to be here. 25, 24 and 77.4. Look at this. 25, 24 and 77.4 will be inside. 2601.4. See, I am taking 42 out. If you take 42 out, inside what you have, 2601.4 into 11. 38 minus 27 is 11. So 11 and 22 can be further simplified. 11 and 22, you get 2 here. Is there anything else we can cancel? 1.3 and 26. Oh, that's nice. Usually in the experimental outcomes, you don't get such numbers. But here we are getting it. That's nice. That's 20. 20. I think that's all. We can cancel this by 3. Or, yeah, 3. 3 will be 1, 4. Here 3 will be 6. Oh no, that doesn't cancel it. That doesn't cancel by 3. So K is going to be 42, 2601.4. From here you get a 7 up there. 7.3, 20, 67.5. This is all we are getting. This is all we are getting. This is around 1300. So this is approximately 2. Right? Check the numbers. We left this 193. 193. Right. So this is little less than 2. Here you have 42, 84. Check this again carefully. 2. Where is this 2? I missed this 2 also. This 2 has to come down. Now look at this. Approximately, see this 1300 into this. If I cancel, this is approximately twice. This bracket and this bracket. Am I right? No, up it is twice. It's approximately twice here. So that 2 and this 2 can be cancelled. Then you have 42 over 193, approximately 0.2 you are getting. Approximately 0.2. 0.2 is the answer you are getting. 0.2 watt meter minus 1, Kelvin minus 1. Or you can say joule per second per meter per Kelvin. Right, that's what the thermal conductivity is units. So when you are giving the answer, make sure you give the answer with the right units. Otherwise, you might lose the marks in the exams. Careful. This kind of, complicated solving is very rare in the exams. But when we do the experiments, it's unavoidable. But it's okay. You can double check these answers with the calculator as well. I think 0.2 is the right answer here. And rubber's thermal conductivity is in the range from 0.1 to 0.4 depending on the type of the rubber. There are different types of rubber, different types of mixes they make. So depending on that, thermal conductivity changes starting from as low as 0.1 to 0.4. So 0.2 is a feasible value, is a possible value for this thermal conductivity of rubber. Clear? Now we will see some past paper question on this experiment. Right. I have taken a very old past paper here, 1989 advanced level paper. The diagram shows the experimental arrangement to find the thermal conductivity of rubber using rubber tube. Exactly the same arrangement we have done. in the diagram, what are denoted by letters A, B, C and D. A is the thermometer. So simple. So simple. Thermometer. B, stirrer. Anyone can answer. Everyone can answer. C is the colorimeter. Colorimeter. And D is lagging. Or you can say thermal insulator. Thermal insulator or lagging. The internal and external diameters of the rubber tube have to be measured in this experiment. But vernier caliper is not suitable for this. Explain why. The shape will change if you put it in the vernier caliper. Yeah. Since rubber tube is not rigid, it will deform if vernier caliper is used. Next, state an instrument that can be used to obtain the above measurements. Which instrument can we use here? The instrument that you can use here is traveling microscope. Traveling microscope. I did not show traveling microscope in this experiment, or rather I did not show how the readings were taken, but I mentioned several times traveling microscope is what we use to measure this. Prepare the list of other apparatus required in this experiment. What other apparatus we need here? Let's see. Okay, what is missing here? The steam generator is missing. Stopwatch is missing. What else is missing here? Chemical balance or 3-beam balance is missing. Write that. 3-beam balance. Stopwatch. Then the meter ruler to measure the length. Then the steam generator. Right. How will you measure the effective length of rubber tube? Extend the rubber tube and measure it with the meter ruler. Extend the rubber tube and measure the submerged part of tubes. Measure the length of submerged part of tube. Next, explain why L should not be too small. I told you why it shouldn't be too small. Then the heat transfer rate will be too small. Then the rise in water temperature will be low. The heat transfer rate, because the area reduces, will be low. The increase in temperature will be low. Either it will be low, or if you want it to be higher, then you have to do the experiment for a longer time. Longer time, the error is high. Why? You are losing heat to the environment. So, the increase in temperature will be low, leading to higher reading error percentages. Earlier also in some experiments I have explained, if the reading error is 0.5 degree, suppose you are measuring 10 degree, then 0.5, 10, it's 5%. But when the reading error is 0.5, that's always going to be 0.5 because the thermometer, it changes 0.5 by 0.5. The marks are there 0.5 by 0.5. So if the reading error is 0.5, if you are measuring only 2 degree, Then the percentage error, 0.5 by 2, is 25%. It's so big. So one method of reducing the percentage error is making sure what you measure is of larger quantity. In this experiment, the temperature of water increased from 30 to 35 in 5 minutes. The total heat capacity of water and calorimeter is 9 into 10 to the power 3. What is the average heat flow rate across the tube during this interval? So let's say Q by T is what they are asking. We can take 9 into 10 to the power 3 is the total thermal total heat capacity. That means MCCC plus MWCW all together they have given it into increase in temperature 5 degrees. In 5 minutes, 5 cancelled, 9, 3, 20, 3000 by 20, 150 joule per second, or you can say 150 watt. Next, the internal and external radius of the tube are 0.5 centimeter and 0.6 centimeter respectively. Temperature of steam is 100 degrees centigrade. L is 30 centimeter. Find the thermal conductivity of rubber. So you know Q by T has to be K A. This is the usual formula. Q by T we have got 150. K we don't know. A 2 pi R. R has to be the average of these two, 0.5, 0.6 by 2 into 10 to the power minus 2 because this is in centimeters, into L. Have they given the L? 30 centimeter. So that's the area, Ka. Theta 2 minus theta 1, 100 minus outside external temperature was 30 to 35, right? So take the midpoint, 32.5 we will take, 32.5 average over D, the thickness R2 minus R1, which is 0.6 minus 0.5 into 10 to the power minus 2. Okay. Now, let's try to simplify things. If we can simplify, this 10 to the power minus 2, 10 to the power minus 2 can be cancelled. Then, this 10 to the power minus 2 and this 0, that will be 10 to the power minus 1. Here you have a 0.1, which is 10 to the power minus 1. So, I can cancel those 3. Done. 2, 2. Done. Anything else? 3 and 150 on the other side. 50. Now, let's rewrite it. 50 equals K into 22 by 7 into 1.1 into 67.5. So, K has to be 50 into 7, 22, 1.1 into 67.5. We'll simplify by 5. This is 10. 13 is 65.5. Now let's multiply and see. Up it's 70. The denominator has to be 13.5 into 22 is 27, 297 into 1.1. 7, 6, 11, 12, 3. 326.7. You get 70 by 326.7. That's approximately, see, 0.2 is, 0.1 is 32.6, 0.2 will be 65. So, it's around 0.21. 0.21. That's the unit. Clear? Right? So, that's the value for conductivity we are getting. In the experiment also, we got a similar answer. Remember 0.2. Yeah, this is also around 0.21. Is that clear? So, This is the experiment. Remember, this is not included in your currently available practical experiments list. Still, I have done this for you because it can be tested in an essay question. So, this knowledge will be very useful when you are doing the essay question. So, whatever, even if it is not in the experiment list, if we think that it is more useful to you in answering some other question, if we think it is possible to be tested in some other section, we have done that experiment for your benefit. Right. So, practice this, try to understand each step we have done. Let's meet up with another set of experiments soon.